previous lecture was about safety grounding and safety in general. Now we will talk about signal grounding. What is that about? As you seen before already this slide, the safety grounding was the previous lecture topic. Now we'll talk about signal grounding, and especially in that signal grounding we will distinguish between digital and analog grounds. And keeping that in mind, we will talk about noisy and quiet grounds as well. So all that is then related to a single point, multiple point, or hybrid grounding. So all that is related to signals and how the noise is spread through the ground and how we can confine it to a smallest possible area. First of all, I have to show a few definitions. What is a ground anyway? The first definition would say that a ground is an equipotential point or plane which serves as a reference for a circuit for all voltages in the circuit or system. So these voltages in this system are reference to the same ground plane. So this is the input voltage, then it is amplified, we get another voltage, and the reference for this voltage is the same, is the ground. Then we have some analog conditioning, we have another voltage here, and then we have some A to D conversion, and now we have digital voltages, and we have the microcomputer, and then we have some communication voltages here, and all of these have the same reference, which is the ground. So the ground can be treated as a reference point for all these voltages. Another definition would be already quite known one, which would define the ground as a low impedance path which carries all the return currents which return to the source. So all the connections, all the signal connections here, they all require a return current on the ground. So the ground serving as an equipotential point also serves as a return path for all these currents. And as you know, these two definitions have a certain property of ground in common. We want the ground to be a low impedance connection. And two grounds on the ground, or 2 points on the ground, are never or really rarely on the same potential. So what we strive to is to minimize the impedance of the ground. And that would serve both main definitions of the ground. Being an equipotential point, serving as a low impedance path for all the return currents. Let me show you a few examples. The first one would be this one here. So we have a power supply. This is connected to a mains socket. Then we have a transformer with all the circuitry around, a power supply defining the power for this amplifier. We have the source voltage here, which is amplified, and then we have some cable to the load somewhere very far away. So we have a powering of an analog circuit that has some ground, and there we have a signal transferred to some load somewhere else. So this is my device, and now what we have here, we have a power supply cable and we have a signal. So a noise can couple to this signal here, to this cable, and then that noise that carries or induces a current that flows to this ground all towards here. And since this is a high frequency current, it can flow through a common capacitance of this transformer, and then it continues its way to the mains power supply. This is quite a common noise path that happens in such a circuits. Where it originates, it even doesn't matter so much, but what it matters is that this current is actually flowing on this ground. And if this ground is not an equipotential it is because it has a finite impedance. So the impedance of that ground determines the voltage drop between these 2 points. And that voltage drop due to this induced current then is sort of acting as an additional voltage. So the signal voltage is then amplified, and the output is the amplification or the gain of this amplifier times the signal voltage plus the noise voltage, if this is the noise voltage here. So this is how a common impedance which serves as of the ground, which serves as an input reference for the power supply, for the signal, for the powering of the amplifier, and for the output signal. This common impedance, due to this noisy current that flows through it, induces a certain noise voltage that is then amplified. So what can we do? Well, by a proper routing, we can get rid of it. So that's the same circuit connected in a little bit different way. So this is the same device. The noise gets into this cable, it flows through here, and it continues there to the power supply. Now what you see here, the noise is routed away from the most sensitive part of the circuit. So there is no additional noise here, and the output voltage is the gain times the signal voltage here. So no noise voltage is present because the routing of the noise is directing that noise away from the sensitive part of the circuit. Okay, so what we can we conclude from here is that by careful placing and routing of the signal, keeping the sensitive parts away from the noisy parts, we can get rid of the main noise coupling problems because of the common impedance of the ground. What else? That's another example. We have a power supply here. The current is flowing to this power source. So we have a power supply current. And we have the output current as well, which flows here. So we have a power supply current flowing directly here. I'll command again. And we have the output current that flows here. So both are actually flowing in the direction where the input signal is. And the output voltage is not just because of that input signal, but also because of this common ground impedance times the currents here. So we have the noise voltage due to the power supply plus the noise voltage due to the output current that might also change the potential here, which is not wanted. The output current, of course, is usually mainly due to the signal amplified by the amplifier, the useful signal, of course. But it may not be beneficial for that current to change the potential of the input voltage. And of course, if it contains some other noisy components, it may influence the output signal by itself. So all that times the gain of this amplifier is present at the output. So again, by careful placing and routing, we can actually get rid of the most of that current or the noise just by putting it in a way that it does not influence the input voltage. So again, by placing the input sensitive part of your circuit away from the noisy part, including the power supply currents and all the rest there is, your output voltage is then free of these noisy signals. So the careful routing and including using the ground planes as a low impedance connections will get all the noise coupling of the ground minimized. So this is a picture which I already showed once, how the ground plane use of ground plane decreases the impedance of the connection by several orders of magnitudes. So, keeping that in mind, keeping also in mind these two examples I shown here, we distinguish different grounding schemes. There are single point connections, like here, where these circuits are connecting to a single ground point in series or in star connection manner. So all these connections of ground are connecting this circuit to a single ground point. So that's why they're called single point connections. But these circuits could be connected in series or in a star configuration. Then we have a multi-point connection, which would be that you use a ground plane and then you connect these circuits to a different points on that ground plane. So which one is used for what? First, all the single point connections, as you see here, first of all, you have to know that why do I show the connections in a form of an inductance? Because I want to show that every track on the PCB has a certain inductance, and that presents the main impedance of this connection at high frequencies. And this is all we care about. We mostly care about the high frequency properties of these ground connections. So that's why I draw inductances, which are then representing the connections. And here you can see that the current flowing through circuit 1 flows to the ground. It forms a voltage drop because of the circuit 1. The current that flows from circuit 2, it provides voltage drop here, but also here. And the current that flows through circuit 3, it will provide voltage drop there, but also here, and also here. So now you see that in this single point series connection, the current that flows from circuit 3 influences the voltage, the ground voltage of circuit 2 and circuit 1. And current that flows from circuit 2 influences the ground voltage of circuit 1, 2, and also 3. Actually, the circuit 1 also defines the voltage, ground voltage of circuit 2 and circuit 3 because it's here. So that means that actually, if circuit 1, circuit 2, or each of these circuits contains some noise, it will be reflected in all other circuits. So such a single point series connection can be used in cases where all these circuits do not contain any noise. And this is also only possible if you have, let's say, analog circuits, low frequency circuits. If you look at single point star connection, then you see that all these circuits are connecting to a single point separately. So noise, or the currents flowing on this ground, I1, 2, and 3, are all influencing each circuit separately and do not interfere with the others, which is a good thing, of course. The problem here is that you have to route every ground separately to a single point, which may be quite hard on the PCB. But in that case, you make sure that these circuits do not interfere with each other. So this one could be a separate analog amplifier, this could be an A to D converter, and this could be a microcontroller. So each one of them would get a separate ground connection. So the question is, why wouldn't we connect all of that like that? Why wouldn't we connect every circuit in our PCB like that? Well, the answer is because we can't, and it wouldn't be practical. And the other thing is, please do not forget about the return currents on ground for high-speed digital circuits. These return currents would then have to flow along a high impedance traces, because that couldn't be done by a ground plane. You have to have traces to connect each ground separately to a single ground point. And the return currents, let's say between circuit 2 and 3, if you can imagine that you have a high-speed connection here, then the return current would flow very, very far away, getting back to the initial circuit number 2. If you have a generator here and you have a load there and you have a high-speed connection, can you imagine that you have a trace that goes all around your PCB to a single point somewhere in the corner, and you have a very, very long return current because of that? And this would then provide a very high radiation of current-induced differential mode interference. And that's why a single point connections are never a good idea when you have high-speed circuits. I'm talking about 1 megahertz. So for low-speed circuits, very sensitive circuits below a megahertz, you may use a single point star or series connection, but not for high-frequency circuits. The reason is very obvious. The return current paths would be very large, and the areas formed by these currents would be large, and they would radiate very efficiently, which we don't want. Therefore, for a high-speed circuitry, we always use ground planes, and we connect these circuits to these ground planes with the shortest possible connections. And these then provide a very short and small return current loops. And very large ground plane then provides a low impedance ground connection. So these two are for low frequency, and this is for high frequency circuits. And we talked a lot about the high frequency grounding already, about the return currents, about signal integrity, about all that. But we did not talk about ground separation and single point connections. And this is what we will do in the next few tens of minutes. So single point grounding is used for low speed circuits below megahertz, even some say below 100 kilohertz. So more or less for audio circuits and for analog instrumentation, our mains power systems, which are of course low frequency systems. Why about analog instrumentation? All these analog signals from sensors that have to be amplified in order to have say decent A to D conversion, then later are very noise susceptible, and any noise that couples into them has to be really, really well suppressed and routed away from the signal inputs. So therefore we have to apply the single point grounding. Let me show you a few examples. This is what I already showed you before. So we have an amplifier that amplifies some signal coming from the sensor or something similar, and the output current and other currents as well can flow here for this part here. So we have to make sure that this input reference is routed in a single point just at the reference point of the input signal. So no common currents should be allowed to run through this part of the ground where the input reference is placed. Doesn't matter whether it comes from the power supply of this amplifier or it comes from some other noisy part of your system. A single point grounding is necessary here, so that the input voltage here, which is reference to this input, is defined at the point where the signal is measured actually. It's much better if you can ground the system on this output side of your amplifier, not at the input side, so that any current from the power supply or from the other circuits is running away from the input area where you have the most sensitive part of your circuit. This is an example how the power and the signal grounds are separated. These are two amplifiers that are amplifying some signal, and all the power currents and as well as the power supply currents for that matter. If I just draw some extra tracks for the power supply here, are all routed separately. So the thing is, all the other currents that might run through the ground are also present on this separate common power ground as shown here. Only these two reference points that are defining the input references for this amplifier are grounded separately. So this would be sort of a single point series connection. So these two reference points are not each separately connected here. They are connected in series, as you see here, and then connected to here. So it would be a series single point connection in this case. But that current is negligible, and that one as well. So they do not provide any influence at all. But all the rest of the currents that might be problematic are grounded separately and then connected in a single point here. Let me show an example of an audio system. It's one small project for a student, that wanted to make a guitar or some kind effect. So he separated the signal ground of his audio signal, which are denoted by these triangles, and the power ground. This is the power supply ground of these two amplifiers, and here is the amplifying part. So it's a very simple circuit, analog circuit, but he took care that his signal ground is not affected by the power supply current, which actually is then made like that. So he did a very simple through-hole circuit, single-sided, but what he tried to do here is that all the power ground pins of the amplifier, which is in this deep 8 housing, are connected separately. This is the power supply circuit to this point where the input signal comes. This is the input signal connection. So that part of the ground is signal ground only. And this is the power ground. And they are separated completely and connected together in a single point. That would be, again, a sort of series connected ground, single point ground. So this example here, single point series connected ground. So the one series connection is here between these components to this point, and this is another series connection of the power supply ground, all connected to a single point. Let me show another example. This is an example of a to D converter. Most A to D converters have a separate grounds for power supply and for signal. Here they are denoted by A, G, and D. This is the power supply ground, see? And the analog input common. This is the analog input ground. So all the signals that are routed here in this area are actually referenced to this analog input ground. So that means that the A to D converter actually measures all these voltages with respect to this pin number 5. Pin number 2 is just power supply ground. So these two should be connected together, but what is important is where would you connect the analog input common point, that ground here, because that one actually should be connected separately to a point somewhere where you measure your voltages. So to a point to which you want to measure these voltages to, because this ground could be on a different potential. I'm talking about power supply. Why? Because of finite impedance of the ground plane and because of all the currents that flow there. So this is an example of this routing system. So let me show you here. Our reference point is here, a power ground is there. I will now switch colors. Come on. I can't switch colors. I can. Okay. Pointer options in color yellow. So let me show you how it is done here. The reference point is grounded to a power ground like that. So now the reference input point has the same potential as the power ground here. Now, where are the input signals? They are here on this connector. This connector has input signals here in 0, 1, 2, 3, 4, 5, 6, and 7. And the ground is there. So all the voltages that are measured are actually measured towards this ground here. So that ground and this ground here should be on the same potential. But actually, they are not. Why? Because there are certain currents flowing here. Let me show you. Here is the ground, here is the via, connects to the top layer. It goes somewhere here, then it goes around there, and maybe somewhere else, I'm not sure where actually, or maybe to here, and then changes layer, and comes to this, to a certain path, comes to this point here. So there is a long way, and this is ground that doesn't share only this signal, but it shares, it is representing the ground for all the rest of the currents that are flowing on this ground. Therefore, you have a problem. A problem is that now the ground has a different potential because of the currents that are flowing here. And these currents are usually the power supply currents of this A to D converter, the power supply currents of all the rest of the system, plus any noise current that may run on it. So what happened here is that our A to D converter measured a few millivolts different voltage than it was applied to the input. And that was too much. So what was the reason? That few millivolts of difference was a difference in the ground potential between this and this point. So here we had a generator of a few millivolts. And that generator has to be eliminated. How? How we eliminated it? We cut this line here and we grounded this pin directly to this ground here. A single point connection was necessary. Another example. Differential amplifiers were used to measure voltage on this MOSFET. I will now change the color of my pen again. Pointer options in color red would be just fine, right? Okay, so this is the voltage measured on this MOSFET by this amplifier. So the problem is that this is ground. This is ground. Now we are measuring voltage here with respect to a ground, but we want to measure exactly voltage on this transistor. So we have to route this resistor directly here. But since it is connected to ground, it's very appealing that you ground it somewhere and you forget about it. And that was wrong. So what we had to do, we had to connect these input resistors directly to a point when you were to measure it. There are several differential amplifiers here. One, for example, is measuring the ground there. So we had to connect it directly to this point when we wanted to measure ground. So grounding it directly here would be a problem, because then you would measure something else. And since the voltage here is a few millivolts again, you can easily have a few tenths of millivolts of difference between different ground points if you measure it somewhere else. And that's quite a problem. And these are the cases where you want to do a single point connection to a point where you want to measure exact that voltage and nothing else. For the rest, it's not a problem. The only problem is ground. Why? Because the ground is everywhere, and therefore you just route it and connect it to the closest point you have opportunity, and usually that's the wrong one. There are several such cases when you have a separate grounds that have to be that, or let's say inputs that are connected to ground, but you have to be careful where to put it. For example, here you measure the output voltage on this capacitor, and you have a power ground here, but this is the sense input, and it has to be connected to ground, but not anywhere directly here, because you are measuring the output voltage on the capacitor, not output voltage on capacitor plus a voltage difference between this and this point. So there are many such cases, and usually the manufacturers of the circuits, of the ICs, integrated circuits, are pointing to these exceptions and are stressing that connecting such inputs is very important to measure the exact voltage which is intended, which the circuit is intended to. These are mostly some current measurements, usually through some shunt resistors where the voltages are quite low. For example, if you have a few milliohm of shunt resistor, can you imagine if you just miss the point of connecting for a few millimeters, you may add additional milliohm to it, which would be a 50% change, right? That's quite a lot. But quite often you encounter mixed signal circuits. And here there is quite an issue sometimes, because it's not very obvious how to connect them. Usually, for example, if we have mixed signal circuits containing analog and digital circuits, and you connect them in a series connection like here, you see that immediately the analog circuit is affected by the digital current as well, because it's flowing here, and the voltage that is applied additionally to this grounding part here contains the digital current as well, and that causes a lot of problems to the analog circuit. Even though you have a separate power supply, the common part of the ground would affect the analog ground as well. So what you can do, of course, you can connect the analog and digital circuits separately and connect them to a common star ground point. So that would be a star connection to a single point of two parts of your circuit, the analog circuitry and digital circuitry. You can imagine that here we can have several components, and here as well we have several parts of the digital and analog circuit, and they are all grounded separately and then connected to a single point here. But there are many issues here which are not very obvious. For example, what happens when you want to connect these two together? Where would the return current flow? Is it okay if it flows so far away? Does it matter? First of all, let's look about a common practice that we use in this type of circuits, which is a ground plane segmentation. That means that your ground plane is not directly, it's not a single ground, but you divide it into different segments. Sometimes you can make more problems than solutions by that. And you have to be very careful when doing that. It's not very, very easy to choose the right ground segmentations. Nowadays, when we have very fast circuits, commonly in every design, more or less, we use the ground plane segmentation really, really careful because of one problem. A problem is here. We have a fast digital circuit, and here we have a digital circuit. Well, they might be both fast. What would you do when you connect them together? The return currents would flow very far away. So this is a no-go. You can, of course, isolate or make a segmentation of analog grounds where you have very, very sensitive amplifiers or whatever here, and you have microcontrollers and very noisy devices here, and then you can separate them so that these return currents are confined in this area and do not interfere with this here. That's okay. But the same question stands here. You have to connect them usually in some sort of way. How would you do that? And the first rule would say, never connect across the split in the ground plane if you have a high-speed signal. Because high-speed signal would always have a high-speed return current path on ground. And by that, you would increase the loop area enormously. And that would give you a lot of problems. Your return impedance of your ground would increase. The area would increase as well. So the radiation would be increased a lot. So you would have a radiation problem, you would have a ground impedance problem, and you would have a voltage drop on the ground as well, much higher. So anytime you have a high-speed connection, always route it across a common area on your ground. Never route it across the gap. So let me show you one example or two. First of all, quartz. Quartz is an oscillator part of your device whenever you have a microcontroller. And quartz is accompanied by two capacitors, and all together is forming an oscillation circuit. We usually want to isolate the ground plane below the quartz so that it is confined to a smallest possible area and grounded here, so that all the return currents that are flowing here are not spreading around, not interfering the rest of the circuit, because that is a continuous single circuit running at continuous frequency all the time. All the rest is doing or working or not working, or sometimes happens, sometimes it's not. So all that other signals might not be continuously present, and that one it is. So you usually make a separate ground plane below it so that it is really confined to the smallest possible area, and also route the signals to make the smallest area here, and then ground everything in a single point to the microcontroller. So that's why the microcontroller usually has a grounding point next to the oscillator pins. This is an example where we did everything wrong. This is the quartz. These are two capacitors. You see they are grounded here. The ground plane is separated there. So all the return currents are flowing on top layer here to this green line and returning there. So the loop area is very large. The return currents cannot follow the bottom layer because there is a ground plane separation completely there, and they have to return back to these pins here, that one and that one. So the solution is here. So we make a separate ground plane. We put the capacitors on the same side, not perfectly, but better. And the grounding, the return current here is the grounding point here is very short. It's not the best way, because we could do it much better, and you may practice your design in your of the quartz design in your designs on the laboratory course if you want to make it better. For example, this capacitor could be turned around, connected directly here. The grounding pin via should be at least put here as well. The wires then, this wire should be moved a little bit further so that the return current for that would be shorter. and so on and so on. But nevertheless, what we want to achieve is to make the smallest ground area here around the quartz and connect it in a single point to the ground pin of the microcontroller. But what if we cannot do that? Let's say, for example, here, we have analog part here, we have digital there. I will now draw in yellow. We have power supply here, and usually the common part of your ground planes is close to the power supply. So you are powering this part, or maybe that one separately. And you have then return currents locally there, but the total DC, I would say, potential of these grounds is defined here. Now, what if I have a connection here? Then, can I work without any return currents? Or can I allow return currents to flow around? Or can I provide them a common return path here? Now, the high-speed signals routed from this part to this part would then have to go around. That's for sure. But low-speed signals may have some return current paths defined here, but not by connecting the grounds together directly, because then the high-speed signals could run through these parts. By connecting the grounds together here, I can make a ground loop, and I don't want to do that. If I make a separate grounds, I always want to connect them in a single point. So I do not connect them in different parts. So what to do then? For example, if I have high frequency connections, I will always connect them across the common area of these two grounds. For low frequency connections, I may provide a return path with some component that has low impedance at low frequencies, such as coil or ferrite bead. For high frequency connections, I may sometimes use capacitors, because capacitors have low impedance at high frequencies. Or maybe I can make a connection with two Schottky diodes. Why would I do that? A Schottky diode has low drop voltage, low forward voltage. I put two, they are connected back to back in parallel. And these two Schottky diodes are preventing these two grounds to have large voltage difference, and they are very fast. So they are providing return currents really quickly. So they are really acting quickly. So the return currents could be high frequency, but their voltage differences are quite low because of low drop voltage. And this is very important when you have high-speed circuitry connected with a high frequency connections, high frequency interfaces, such as A to D converter. An A to D converter is a quite important component nowadays. You know that in A to D converters, what you have a digital part and you have an analog part. And these two parts are in the same chip. So it's very important how you deal with it. And you have to make sure that the digital part is separated from analog. So the question is how to do it correctly. And this is also the case almost in every circuit nowadays. When you have a mixed signal, you will always have an A to D converter, and it will always have an analog and digital part. So you have to do it properly. An A to D converter, as I said, has a digital and analog part always, and they have usually, not always, but usually they have a separate digital and analog power supply and digital and analog ground. And the names, the labels on the pins always correspond to the internal circuitry to which they are connected. So the digital power supply is connected to the digital part, analog is connected to the analog part. Sometimes people think that if you have a digital and analog power supply, that you always have to separate it because that's what the name means. But it doesn't. How you connect them, it depends on different parameters, on different circumstances. The names of the connections and the grounds on the component are only telling you to which part they are connected to inside, and not how you connect them outside. That's important to remember. Now, what is the problem here? The digital and analog part are very, very close together. That means that there is some capacitance inside the chip between those two. So if you have a noise on the digital section, it will couple to the analog section as well. So what we have to provide is that we provide the least potential between digital and analog ground as possible by properly connecting outside. So that if these potentials are kept close together, I'm talking about grounds now, then the voltage change here would be low and the transfer through the stray capacitance would be also low. And that's the most important design criterion. Keeping the potential between digital and analog ground of the A to D converter as low as possible. And therefore, the noise would not spread inside the chip. So what we actually do in the case of A to D converter is that we put everything on the analog ground plane. Well, the thing is that that is not always the case, but if the A to D converter contains minor digital part, that means that the digital part is not that noisy, then you do that. For example, in this case, what we have here, we have some analog signal conditioning. These are some analog amplifiers and stuff that are preparing the signal for the A to D conversion. So we have A to D conversion here. The analog power supply is here and here. Then we have some filtering, and then we have a digital power supply. We have a local decoupling capacitors, which are providing a stable digital power supply. And all that is connected to an analog ground. Then we have a microcontroller, and we have a high-speed bus there, which connects to the data converter. So we have to provide the return currents of the digital interface. And the digital interface is connected to a separate ground. Why? Because there is a lot of digital currents flowing here, and we don't want them to spread around too much. So we provide a separate ground for digital part. And then we connect these two grounds together close to the power supply. So these two grounds are already connected together. But we cannot afford that the return currents of this digital interface are flowing that far away, because then we have a noise problem. And for that reason, we put two back-to-back connected Schottky diodes. Like that. And these two Schottky diodes are then providing a return currents for the digital interface, for the digital ground. And they are providing a low impedance return current, and they do not allow large voltage differences. And they prevent ground loops, which is the second important thing. The ground loop now is not made because these two grounds are still connected to a single point. What about here when you have a lot of digital parts in the data converter, such as sigma delta, which has a significant digital part and very minor analog part? In this case, the digital part of the data converter is very noisy, and therefore we have to provide a separate power supply and ground for that one. But not to forget, these two grounds are connected to the start point here. Therefore, we have to put two back-to-back Schottky diodes there to allow or to minimize the voltage difference between these two grounds close to the data converter. So these are just two examples of how we separate grounds for analog and digital part of your circuit. The next ground separation that might be also very important is the ground separation because of the electrostatic discharge. What is that? Usually when we have connectors, these connectors are prone to the ESD, electrostatic discharge, when you discharge high charge which you carry around on your body to a connector. So we have to put some sort of a protection devices. You remember we had protection devices in case of USB connector and also others. So these protection devices then are usually combined with some resistors and other capacitors maybe also and other components, so that main charge current is routed quickly and to the shortest possible path back to the ground of your connector. Okay, good. So what we have to really provide is to isolate this high speed, high voltage pulse away from the rest of the circuit. In case of USB connector, for example, we want to route it directly to the shield. That means that whatever you do with your connector, your ESD pulse should be routed back to the shield of your cable. So what we do, we put a protection diodes and we ground these protection diodes to the shield of your connector. And in order to provide the return currents that might be happening on the ground of your circuit, you provide them through the parallel RC connection. Now this ground, the shield, is grounded separately, see? And then, so this separated ground around this connector is connected in a single point through this RC connection to the rest of the ground of the circuit. So all the ESD impulses that are routed to this ESD protection diode are then returning back directly to the ground here of the case of the shield of this connector, and all the high-speed currents that might run on this rest of the ground are not running or conducting or changing potential of this shield of the USB connector. So this is a separate ground of the shield of the USB connector that is connected in a single point to the rest of the ground of the circuit. So this is the single point where the ground of the circuit, the board ground here, is connected to the shield together with the ESD protection. So the ESD pulses are routed directly back, and we have to provide a low impedance connection of these ESD diodes towards the shield of the USB connector. This is example of a USB host where we have the USB connectors here, and this is the metallic panel, metallic chassis, and all these shields of these USB connectors are directly connected to the chassis and grounded by that. So all the ESD pulses that are generated here are then directly routed to these chassis, which is grounded to a safety ground at the end, because this is a part of the computer. And all the connections that are going away from the USB are then separately or separated with the ferrite beads, so which are providing high impedance for the high frequency connections. And these ferrite beads are then acting as a filters for noise generated inside the PCB, as well as the filters for high frequency ESD pulses that may generate from the outside. The ESD protection diodes are even not shown here. What about the protection ring? Sometimes you see in your designs that they use so-called ESD ground protection rings. I would say in older designs this was quite commonly used. Nowadays a little bit less. But how do they work? What is their purpose? The thing is that you want to separate the edge of the PCB with a special ESD protection ring, which is grounded to the case. If you have a metallic case with these mounting holes. So these mounting holes have now screws which are connecting this ESD ring directly to the metallic case. Which means that this protection ring is trying to provide a low impedance path for electrostatic discharge currents that may occur. For example, here you have a connector, and this connector is then having a cable. Now the ESD pulse is generated here because you touch it, and then it is routed here inside, and now you put an electrostatic discharge protection diode here, and then this ESD charge is routed to the, instead of going inside your circuit, it goes around and then it's spread, and it is routed towards the metallic case. And if this metallic case is grounded, then all the ESD currents that might occur on different parts of your circuit, when you maybe have different connectors or some other parts which are exposed, are all routed to the nearest mounting hole here or there. And by that, you actually isolate the internal ground plane away or from these ESD currents that might change its potential. Because you don't want ESD current to run through this middle part of the circuit, because it will change the potential, or let's say it will induce such a big voltage difference that it may even break the components. I've seen capacitors that exploded because of the ESD currents. And this is quite important, that you try to get or to isolate your circuit away from these ESD currents, and the ESD protection ring, ground protection ring, can make separate ground connections for all the ESD currents that may occur or come from the connectors, which are usually at the edge of the board. So this is an example when you have a signal coming in. This is an ESD protection component, a ground, but then this has to flow towards a common ground. Let's say this is a common ground of your inner plane and the ESD protection. Now, because of this length, you may have a voltage difference, and that voltage difference is also then here. So your ESD protection is not as good as it might be if you connected directly here. Now, therefore, sometimes you want to put another ESD protection device just next to your sensitive component, just to get rid of that in additional or residual voltage difference because of this length. Well, therefore, you have to provide really, really low impedance of that ground ring, which means that it has to be wide enough. And you can use several layers. If you have multiple layer board, you may use different layers for the ground protection ring. Maybe you can use all the layers you can, and you can also connect them together with wires. So you want to provide a really low impedance protection ring for so that the current pulses that are drawn by this and conducting through this protection ring should provide the lowest possible voltage differences. But it's still better than current that runs directly through the whole PCB. But in doing all that, you still can have a lot of problems. For example, here it's a ESD protection ring for a PCI card for the computer. And here there are two mounting holes, and here you put a front panel. Now these are the connectors here and here. Now this Esd protection ring then routes the Esd pulses towards these two mounting holes, which is then connected to the case of your computer and grounded. Now, what about the return currents that may flow here? They cannot flow, can they? Well, it depends what kind of signals you have. If you have, let's say, SATA ports like in this case here, they are all differential signals. So ideally, no common mode current is flowing here. But you still have to provide some sort of common connection between this ground plane and that one, which can be done by a small resistor or a ferrite bit or a similar component that just determines the or sort of defines the DC potential of these two grounds. Sometimes when you have a connectors that do not have differential signals, so they are single-ended signals, then you have to be really careful, because then you have a lot of return currents flowing through here. So sometimes the separate Esd protection ring is not advised. In this case, it's certainly not. Okay, by that I would like to finish. After this lecture, you should be able to select the most appropriate grounding technique. So for analog low frequency currents, we have star connection. For digital currents, we have multi-point connection and the solid ground plane. You should be able to design the PCB layout according to that. You have to also design a split ground in case of splitting the, let's say, the ground around the quartz to the rest of the ground, or maybe ground plane of analog and digital part of your circuit. And you can also should be able to recognize a grounding fault. If I show a PCB that has a problem in this grounding, you should be able to recognize it. For example, we have a digital and analog grounds, and they are connected together in several points, which actually does not make any sense after all, because we have a ground loop. These are some links and books that you might check out for that topic. And to conclude this lecture about ground planes and split ground planes and signal grounding in general, you should be careful when you are splitting grounds, because what you do when you split grounds, you always increase the impedance between two grounds. And if you have a ground on one side and on the other side, and you increase the impedance between them, then you may have to make sure that there is no high-speed current flowing through that part of your ground. Because if it does, then you will increase the voltage difference between these two grounds. And that's not good. Because if you do that, and if you connect the cables to it, then you get a so-called common mode generation, or a current generated common mode interference. Again, I talked quite a lot about that, and I'm repeating that quite a lot. So I want to be really clear, just to finish here with this. So if you have two ground planes that are separated and connected in a single point, and you have a high frequency current that runs between, let's say, two components and returns here and contains high frequencies, then you would induce a high voltage difference. And then if you have one cable here, the other cable there, then you have a nice dipole generator with two cables extending as two antennas. So we have a lot of radiation that would radiate towards the infinity, I would say. So splitting ground planes should be really, really careful. Better not do it if you anticipate that you would have some high frequency current flowing in this range. And nowadays, when all the circuits more or less contains high frequency digital parts. Splitting ground planes, it's not that common practice anymore.